So at this point, I wanted to do what I usually want to do when I attack a problem. It's time to play with Maple. So I did some programming. Let me see if I can pull up my Maple worksheet. The projection should come on in a second.
So your circle out there is a conic section.
Yes.
Your hyperbola here is a conic section.
Yes. Yes.
So a general setting might be doing this on conic sections.
Yes.
Generally, like the parabola.
Right. Yeah. Yeah. The distance is different, and so I don't know what that how weird that makes stuff. But anyways, so let's take a look at. Yeah, this is kind of what I did when I wanted to play around with it. So the first thing, we have to write a procedure that finds Minkowski distance. So that inputs. Can everybody see this just fine? Or do I need to make it bigger? Okay. So Minkowski distance. So that does exactly what it says. So let's just come up with some sample points to try to play around with. So these are all points on hyperbola, and for the time being, I'm sticking to the right branch of the x squared minus squared y squared equals +1 hyperbola. And so those are all those points. If you don't believe me that they're all in hyperbola, we can define an origin and then check all our distances from the origin. One's all the way down, so that's a good sign. And then let's go ahead and plot these points. So there they are. It was not clear they were on a hyperbola. Let's plot the hyperbola and put them all on the points. And once again, order is very important here. So I didn't label them, but this is so 0.1, 0.2, 0.3, 0.4, 0.6. So here we have 6 points all on the same branch of the hyperbola in the proper order. So that's good. So the next thing up is let's find the distances between all the pairs of points. So that took some copy and pasting so that D12, D13, so on and so forth. It's just the D12, just the Minkowski distance between P1 and P2. And so let's actually check some theorems. So here is Ptolemy's theorem. So we're calculating out each side. So D13 times D24, and the other side. And lo and behold, these are close enough up to round off errors, so that is quite comforting. We might as well play around with some different points, check it again, so it still holds. Let's check the ratio version. So this is the n equals 4 version of McDougall, still nice and close. Furman's theorem, McDougall's theorem in the case n equals 6. So all the way down, we are getting essentially the exact same answer up to, it's only in the last digit or two. So this provides very strong evidence that yes, these theorems are going to hold appropriately in the Minkowski plane. Okay, so that's all well and good. But the question is, we put all our points on the right branch of the hyperbola. Why else we put points on the left branch of the hyperbola? So let's try that. So here, just some small changes. You'll now see P5 and P6 are going to be negative in their x coordinates, so they're going to be over on the left-hand side. We'll plot them again. So 4 points on the right, 2 points on the left, and there we can see them. And so here our ordering is now 1, 2, 3, 4, 5, 6. So and again, ordering is very important here. So let's recalculate all the distances. We did that. And so Ptolemy's theorem, okay, so we're still stuck only on the right-hand side, so that's not too interesting. But here's our first one. So now we have some points on the left and some points on the right. And that seems to be holding. We saw that before, but here's Furman's theorem. So this is all 6 points are being used, 4 on the right, 2 on the left. That seems to check out well. And then McDougall's theorem, that for in the case n equals 6, that is also working out. And of course, we can just play around with this. For example, the question is, when we're trying to figure out which order to put these points in. You know, it's not immediately obvious whether we go, so we go this way, should we go this way or this way on the right branch? Or sorry,
the
on the
geometry
branch.
tells you.
What was that?
That's forced. Geometry.
Yeah, but you know, you can think of what's going on here. We can just play around with maple, you know, just for here. So now I just put P5 and P6 in the opposite order. And when we recalculate the distances, we can see very clearly that that no longer holds. So maple is very important here, just in terms of getting some intuition. And I said I'm not a geometry by trade, so maple is going to be my guide in figuring out what is going to be true and what's not. What things should I be attempting to prove and what things should I not be?
What genres would be?
Yeah, I mean, there's no real difference between the two branches of the hyperbolic. You go up there and you come in from infinity, and you go up the other one.
Yep.
It's just one
Yep.
branch, really.
Yep, and
So that's using human intuition.
yes.
It's cheating.
No, it's classical geometry.
So the question is, what happens about the top and bottom branch? You know, so can we put points over there as well? And so here I'm putting 3 points on the right one, and I'm putting 1 point on the top one. So there's our plot. And so when we find the distances, and we try Ptolemy's theorem, and it doesn't work. And the ratio version doesn't work. So you know, this says we should only be looking for theorems that stick to like the x squared minus y squared equals 1. We don't try to put points in both the plus
Well,
and
it would be
minus.
like taking two circles
Right.
for Ptolemy's original theorem.
Right, yeah, and so
It's not as hyperbola,
Yeah.
because different distance. You know exactly.
yes.
Or maybe.
Some sort of like two different units, or like.
Yeah, so it feels weird. Again, I do not have intuition about this sort of thing. This is where I get maple to help me build my intuition as I have people explain to me what is going on. So anyways, this does give us pretty good evidence to think that we can prove.
So maybe
these
the
theorems.
universal translation like this one?
I'm sorry?
Maybe the universal dictionary like this one, from Minkowski?
Yeah. So what we're going to try to do is try to come up with a unified theory of this to show that whenever we have a Euclidean theorem, it also holds in the Minkowski plane, and we're going to be using those ideas that are slowly appearing under the screen. So let me bring down the blackboard. Okay, so let us suppose we have a Ptolemy-like theorem. Hopefully I won't have to define that in Euclidean geometry, and our goal is to show that it holds in the Minkowski plane. So let us just formally define some stuff. So if we fix n is bigger than 1, we let f be a polynomial, and choose two variables corresponding to the diagnosis and side lengths. And so once again, we're going to have E, and then we will have M. So this is a set of polys for Euclidean, and same thing for Minkowski. So these are just polynomials such that whenever we put points on a circle and arrange them appropriately, and plug in the distances, we'll get 0. Okay. So let's try to think about what if what properties f must have to be in E. So take f in E, and we want to substitute in xjk equals the djk, and we're going to use our definition, or our version here of minus I times uk squared minus uj squared all over uj uk. So that is what we came up with back up here. And so let us call, so put everything over a common denominator, and then factor out the minus i's and stuff like that, and so call numerator f star. And so the claim is that f star has to be identically 0. And so in order to, a little bit low on time, so I would just kind of talk through the proof. Basically, it's just because it has so many zeros, like any set of points on the unit circle, arranged appropriately, provides a 0 for it. And so, these are polynomials, so enough zeros, it has to be identically 0. So we will take that. And so it would be nice to have a similar sort of substitution in the Minkowski case. And so let's discuss what that might look like. So following our nose, we put over here, we have a nice standard form for the Minkowski, or for the just a regular circle in Euclidean space. So let us see if we can do the same thing over here for Minkowski. So we're going to arrange these P1 out to Pm, and so for these, we're going to say it's defined as cosh of 2sj, sinh of 2sj. So those are all on our hyperbola. These are all on the right branch. And then starting from n plus 1 out to Pn, we are going to put these all on the left branch, minus cosh 2sj minus sinh 2sj. I don't need the minus sign in here, but it will make our work a little bit easier. I should say, how do these s's relate? So s1 is less than s2, sm, and now the s's go the other way on the left branch. And so when we try to do the calculation that mjk, when we try to do this sort of thing, I'll skip the details, but when we define Vj to be e to the sj, so over there is e to the I tj, here's just e to the sj, we end up with vk squared minus vj squared all over vk vj if j is less than k is less than or equal to m, if we're staying on the right branch. If we are staying on the left branch, then it's the same thing, but with a minus sign thrown in. So if j is bigger than m, so that's two cases, and the third one is what happens if we cross over. And so if we end up crossing over, oh, and by the way, so this Vj is if j is less than or equal to m, and then if we go to the left branch, Vj is e to the minus sj, just to make things work out a little bit easier. So we have two cases, now we just have to do the crossover case, and this is the annoying one. This is the not fun one. And we end up with a plus sign in between the two. And so this happens if J and K are on opposite sides of M, if Pj is on the right branch and Pk is on the left branch. So what can we do here? Well, we stay on the left branch. This is our formula here, and so the amazing thing is, we can just plug this into our formula, and we don't care what these Vj's and Vk's, we don't care if these are e to the sj's or over here e to the itj's. It's just a polynomial identity in these Vk's and Vj's. And so, just like that, we get 0 automatically. If we stay only on the left branch, same thing. We have to, there's a little bit of mumbo jumbo we have to say about homogeneity to take care of minus signs, and we do have to be a little bit careful about that, but we can take care of it. It just is this one case in the middle that we're still working on this. We're trying to make this work out. So we're think very strongly it's true. For any given case, if a Furman's case or something like this, you can check it with a computer, expand everything out to see that it works. But as of right now, we haven't been able to get this using the more general, or using the fully general thing. So it's kind of depressing to end the note on a little bit of downer, what we haven't been able to do, but I guess that's what I'm going to do right now. So thank you all.
Thank you, Alexander. Quick question.
Only a quick comment. There is a book that's called The Geometry of Minkowski Space. It's a credit text.
Okay.
I don't know whether you know about that. That
Yeah,
might be useful to look at.
Yeah, I did have one reference that I was using to help me out, but I will see to look it up. So geometry of Minkowski space.
Geometry of Minkowski Space.
Okay.
I think it's a mistake to call this Minkowski space. It's a hyperbola you're working on, and that's a
No,
conic section.
But
Yeah, but
he uses
the
a
metric
Minkowski
is-
metric, the metric in quotes. So
That's
that's
symmetric on the hyperbola.
Yeah, but
No, no
You've
point.
never left the cone, right? All your examples have been two-dimensional on the cone.
yeah, that's true. He restricts it to the unit curves. Yeah, but
So I
in
think you'll
general,
probably
of
get a
course, it's
general
not
proof.
real metric.
Yeah.
But you don't have Ptolemy, it's not on general quantum section. Ptolemy is only on a circle. So he's trying to have a dictionary like they did for general, for all these class of theorems.
Didn't Valentine do it, you said, on the elliptics? Didn't he do it on the ellipse, in effect?
So he was, let's see, so he was working on, and he did it on the surface of a sphere, put circles on the surface of a sphere.
One circle.
Yeah, one circle.
No, Ptolemy is only on a circle, not an ellipse.
It might be a situation where you have to define your metric different. Like it might be true on the ellipse. Maybe you redefine your metric to make things work out.
Yeah.
So perhaps there is something there.
Or saying, so it may follow from this.
Yeah, sure. Do it on the conic section. in general.
Okay.
Okay, good
Okay.
suggestion.
Thanks a lot.
Okay, thanks again. Thank you.
Thank you.